Also, the third homework should be put up today. It's due after the midterm. But you can always ask questions during the office hours on how to approach the problems. I'll give you an idea of what the midterm problems would look like. So, in today's lecture, we'll finish up the TCP connection management principles, and then we'll look at how flow control and congestion control is implemented in TCP. So before we start doing that, let's just take a look at the TCP segment structure again, and that will tell us how the different fields are used and how they are exploited. So to understand how the connection management and flow and congestion control work, you have to look at these different fields: the sequence number, the acknowledgement number, the receive window, and the bits or the flags which are here. So there are flags like R, S, F, and A, which are very important for connection management. So A indicates that this particular packet has the acknowledgement field valid. S indicates that the SYN field is valid. F indicates that the FIN field is valid. R is RST. So we'll see what these mean. So let's look at the connection management principles again. So in your assignment, you have been using TCP. You have been opening up sockets, and these sockets you open in the application layer. So what are the events that happen in the transport layer to make this connection live? So TCP connection management has a three-way handshake. In this three-way handshake, the first step is initiated by the client. The client is the one which is going to initiate this connection, and that sends the server a TCP SYN segment. So what's a TCP SYN segment? It's a TCP packet which has no data, but the SYN bit is set to 1. So that's the first packet that is sent in any connection. That is the first part of the handshake. A client is going to send a TCP packet, no data, SYN field is set to 1, and the client will also specify the initial sequence number. So initial sequence number, you remember initial sequence number, the sequence number and ACK number indicate what is the next packet to be that one end of the connection is expecting, or the next byte one end of the segment is expecting. And what is the last byte that connection has successfully received. Once the server host receives this SYN, then it's going to reply with a SYN ACK segment. So again, this is a TCP packet with the SYN field, the S bit set to 1, the ACK bit is set to 1, and no data. And at this point, the server is going to allocate buffers, and the server will also specify its initial sequence number. In step 3 of this handshake, the client will receive the SYN ACK packet. Once it receives that, then it replies with an ACK packet. So now the SYN field is not set to 1, but the ACK field is set to 1. And now this third packet may contain data. So no data transfer occurs until the third step of the process. The third step, the ACK packet will piggyback data with it. Now in this process, do you see anything which seems sort of redundant or strange? Any step which you might think is not needed? Now this is remember, this is the initialization of the connection. So this is where the byte streams are going to start transmitting between the sender, between the client and the server. Yeah.
The second step maybe, because if you send out a request to the connection, all you need is by acknowledging that the server has opened the connection and verified that.
So that's what the second step is doing. So these individual steps are all needed, but within these steps, look at what the client does and what the server does. The client is specifying an initial sequence number, and so is the server. The question is, why is this initial sequence number not 0? Why do you need to set it to some value and inform the other end? This is done for security reasons. So in any TCP implementation, the initial sequence number is set to some random value at both ends. So you never start a connection with initial sequence number set to 0. You set it to some random value and then you proceed from that random value. Why do you do that? Because an attacker can spoof a connection and it can take over in the middle of a connection. So suppose an attacker is able to guess the initial sequence number. Suppose it's always 0. Then the attacker can spoof the sender IP address, take over the connection, and handle all data transmission between the real client and the real server. But if this attacker does not know the sequence number, then when it's trying to take over some connection, because the sequence number is not known, it's random, the server is likely to get confused and the probability of an attacker taking over a connection is reduced. So this problem was realized a few years back, and since then the initial sequence number in both cases is set to some random value, and then it proceeds sequentially from that random initial sequence number. So that was the connection setup. The connection closing, when you close a socket in your application layer, the steps that happen are the following. Suppose a client decides to terminate a connection, or everything that the client wanted to do has been done. Then what the client is going to do is it will first send a FIN packet to the server. So the F bit is set to 1. When the server receives this FIN packet, it will send an ACK acknowledging that FIN packet. It will close its socket connection, but it also sends its own FIN packet. When the server sends the FIN packet, the client will send an ACK packet and it will wait for a timeout interval before closing all connection. Why do you need this timeout interval? Yeah.
be delayed by the network, which is arrived late.
Which packets might be delayed?
Some of the packets sent by the client or server might be lost in the network.
So if there is packet reordering and there are still some packets which are somewhere floating around in the network, the client and the server have to make sure that they are absorbed into the connection. So that's why a timeout interval is kept before closing the socket and removing all the buffers at the client or the server. Another problem that could occur is the acknowledgement sent by the client might get lost, and the server here is waiting for the acknowledgement. So to take care of the acknowledgement getting lost, the client also waits for a finite interval before closing the socket, terminating the socket, and releasing the buffers. So that's how the connection management proceeds. Between the three-way handshake and the FIN packet being sent, data transfer occurs, and we saw how data transfer occurs with the ACK, the data segments, the ACK values, and the sequence numbers. Another thing that is done in this connection management process is when the client and the server send out the first packet, the SYN or the SYN-ACK, another field that is set in the TCP segment is this field receive window. Receive window is the number of bytes a receiver is willing to accept, and both the client and the server inform the other end of this receive window, and this receive window is used to do flow control. So now let's look at what are the issues involved in flow control and congestion control. So where do you need flow control? Yeah. At the endpoints to rate match the sender and the receiver. So if you have a sender here, and data is, let's say, transmitting in one direction, the receiver can absorb data at a certain rate. So the way you can imagine this process happening is, let's say this is the TCP buffer, data arrives from a lower layer, let's say IP, the network layer, and then data is sent to the application layer. The rate at which this receiver can send data to the app layer defines the rate at which it can absorb data from the IP layer. If the incoming data rate is higher than the outgoing data rate, then this buffer which TCP allocates is going to grow and overflow. You don't want that to happen. So the way it's done is TCP at the initial connection phase will inform the other side what the size of this buffer is. And the sender will make sure that the outstanding packets which are in the network never exceed the size of this buffer. So now what happens? Let's say in the initial connection phase, each side informs the other side that my buffer is 4096 bytes. Okay, that's the size of this buffer. Now TCP sends a packet out. Let's say the size of each packet is 1K bytes. So how many packets can the sender send out? About 4 packets, roughly 4. So 4 packets. Four packets go out on the network, and then acknowledgements are going to travel back. Okay. Yes. So each of these acknowledgement packets, they are also TCP packets. So they'll also have the receive window field. Now, if this the application layer is very slow, this transfer is very slow, then when the first packet arrives, when the first data packet arrives, it's going to fill up, let's say, 1/4 of the buffer, because the application layer has not absorbed this packet. So when this ACK goes back, what's the receive window going to be? The receive window is going to be 4K minus 1K. So it's the available buffer. Available buffer at the receive end. So once it has received the first packet, it will send out the first ACK, but it will reset the receive window from 4K to 3K, because it has only 3K available. It cannot absorb anything more. The second packet arrives, and if the application layer has still not absorbed that data, then the second ACK will have the receive window 2K. When the third packet arrives, suppose now the application layer has absorbed these 2 packets, then the third ACK might contain 4K or 3K, whatever is the free space available in this buffer. So the receive window fluctuates according to how the buffer is filled up, and that way the sender never sends anything out on the network which the receiver cannot absorb. So flow control is achieved by managing this receive window. This receive window dynamically adjusts according to the buffer space available at the receiver, and since the sender is never allowed to send anything beyond the receive window, the receiver buffer is not going to overflow, and this principle applies in both directions. The data packets that are going also have the receive window corresponding to the sender side. You got a question? Okay, good question. So suppose the application layer is really slow. All these 4 packets fill up the buffer, and the last ACK that goes out for this last data packet, so let's say ACK number 4, it will have receive window equals 0. So receive window which has gone out is 0. Now the sender is not allowed to send anything out, because the receiver is saying that I cannot absorb anything more. Now you have entered a deadlock. The only way the sender can know if the receiver is ready is by getting an acknowledgement field back. Right? Eventually, this app layer will absorb all these data packets and this buffer will clear up. But how does the sender know about it? The last ACK that was sent made the receive window 0, so the sender is not allowed to send anything. So you have encountered a deadlock. How do you address the deadlock?
I'm sorry? Wait. And then send it again. Hopefully.
How long do you wait?
Well, you can sort of gauge from the speed beforehand, like transmission rate. Yeah.
So you use the timeout interval? That's one way to do it, but how much data are you going to send out?
Well, as much as you can send before the same time. You have to adjust the rate of receiving.
Once the server observes all the packets and hasn't received anything from the client, it sends some sort of keep-alive packet to make sure the client is still there. In which case, the client will know that it's available.
So now you're making, you're shifting the responsibility to the server. Well, the server
Someone's going to make sure that the other person is there, or else they'll just close the connection anyways.
Right. So what happens in the TCP specification is if the receive window is set to 0, then the client or the sender is allowed to send TCP segments with only 1 byte of data. And once that 1 byte of data makes its way through, then the acknowledgement field will have the receive window. So if the receive window that is received at the sender is 0, then the sender can send across data packets containing only 1 byte of data. And if the receive buffer clears up, then the sender will get that information and can transmit larger window sizes. Yeah, this slide explains the process. Data is arriving from the network layer. The receive window is the receive buffer minus data in the buffer, and that is constantly being updated and informed. The sender is being informed. Now we get to the principles of congestion control and the way TCP implements congestion control. So flow control provided this rate matching between the sender and the receiver, and really rate matching between the rate at which the sender application can generate data and the rate at which the receiver application can absorb data. So that's the task of flow control. When is congestion control needed? Yeah. Never, yeah. So congestion control is when the network cannot handle the rate at which the sender is sending data. So now that's doing a speed matching between the sender and the network. If the network has a lot of traffic and you're sending data at a certain rate which the network cannot handle, then these packets are going to be either delayed or dropped, which is a sign of congestion. And congestion control tries to address that and limit the rate of the sender so that you do not cause further congestion in the network. So when can congestion occur? Well, you have a bunch of different senders all going through a shared link. The link is going to aggregate traffic, and the outgoing link may not have enough capacity to satisfy all these packets. So your incoming rate at a router or a link, the aggregate incoming rate is higher than the outgoing rate, and this can occur at any point in the network. Now, flow control in TCP is a much simpler problem than congestion control. Why is that? Think of what is the purpose of flow control? The purpose of flow control is to rate match sender and receiver. So the only players in this game are the sender and the receiver, and they are talking to each other. So they can explicitly inform each other of what is the rate that I can handle. Congestion control, on the other hand, is doing a rate matching between a sender and the network. And the players in this game are millions of all these flows which are sharing this network, and all the routers, all the links which a flow might encounter in its path. So when you start downloading a web page, your computer has no idea how many other links, how many other flows are sharing the link that you're going to go through. So how does your computer know what rate to set your connection at? One way to do it is the first router on your path keeps a track. Okay, I have 10 flows going through, you're the 11th one. My rate is 10 megabits per second, so you're going to get 10 whatever divided by 11. What is the problem with that approach? It's not scalable. If you have hundreds of thousands of flows, then maybe at the first hop you have only a limited number of flows, and the router can do per flow accounting and keep a track. But as these flows go into the core of the network, where there are millions and millions of flows, you cannot expect the routers there to keep track of the number of flows. Plus, you're trying to do this congestion control at the transport layer. The network has no idea of what the transport layer is doing. Routers in the network implement everything only up to the network layer. So routers in the network are not even going to look at the TCP headers. They have no idea what's going on in the transport layer. So the problem of congestion control is very difficult because you don't have an accurate picture of what's going on in the network. Flow control, on the other hand, is very easy. Because all the parties involved in flow control talk to each other explicitly, inform each other explicitly of what the rate the other party should be sending at, it can be implemented fairly simply. Congestion control, on the other hand, is a very difficult problem. So how do you implement congestion control? So what are the unknowns? For congestion control? Unknowns are the, well, number of links, bandwidth of the links, these are all the unknowns that TCP has to deal with. When TCP initiates a connection and you go through the three-way handshake, you have no idea that underneath the transport layer how many links your flow is going to go through, what is the bandwidth of the links, and what are the other flows, or how many other flows are sharing those links. So to get an idea of what kind of bandwidth you can get, you need to know all of these quantities to get the exact answer. But if you don't know the exact answer, what do you do? Yeah.
Yeah, you're on the right track.
Start the initial rate.
Yeah.
And then see the upgrade range. And if you get slow upgrade, you start seeing the lower.
So you're saying send data at a certain rate and look at the rate at which acknowledgements are coming. So you have two scenarios. One scenario is the other end of a connection is, let's say, going through some satellite link, but no other flow is sharing that link. Now because you're going through the satellite link, your round trip delay is going to be large. So your acts are going to be delayed. Right? So that is not the exact answer. You have to do something else. So there are two approaches. You're on the right track, yeah.
How about if the ACT packets include the receive time of the sender?
The R packets,
That way you'll know how long, you won't know what the round trip time is, but you'll know how long it took for your packets to get to the receiver.
okay.
If you look at the TCP segment, it does not have timestamp field. So even if you could use that information somehow, it cannot be implemented. The only way you can calculate the time is at either end of the connection. You can only get round trip time estimates, not one-way delay estimates. Yeah.
Should we consider the number of packets dropped?
Okay.
Should we consider the number of packets dropped? So to go from getting an idea of the unknowns, what are the effects of congestion? Yeah. Effects of congestion are two. One is what you were talking about is delay. Queuing delay. and second is packet loss. When the queuing delay becomes so large, when the buffers become full, packets are going to be dropped. So both of these things, delay and packet loss, you can sense at the sender or the receiver. So you can sense if congestion is occurring in the network by measuring these two. So what you do, what TCP and different variants of TCP do, is they try to estimate the level of congestion in the network by looking at the delay or packet loss and adjusting the rate accordingly. So what TCP does is it probes the network. You start off with a certain congestion window, then you slowly increase the congestion window until you either see that the delay of the round trip delay is significantly increasing, or if the packets start getting dropped. If packets are getting dropped, then you sense, okay, that there is congestion, I must reduce my rate. So at that point you reduce your rate, and then you start probing again, you start increasing again. Why do you do that? Because when this packet loss occurred and you reduced your rate, then in this meantime some other flows might have left the network and the congestion might have cleared away. So that means that there might be additional bandwidth available in the network that you can reclaim. So you go through this cycle over and over again. You probe, you increase your rate. As soon as you sense that there is congestion, you reduce your rate, and then you increase it again. That's the basic philosophy or the theme of TCP congestion control. Now let's see how it's implemented. Have you heard of different kinds of TCP variants? Have you heard of a term like TCP Reno, TCP Tahoe? Nope. Okay. So the way TCP interprets congestion, you can use either the packet loss as a feedback signal. The network is telling you that it's congested by observing packet loss or by observing round trip delay. So TCP variants which use packet loss as the congestion indicator are TCP Tahoe, TCP Reno, New Reno, and TCP SAC, which is really a variation of New Reno with selective acknowledgement. So these TCPs use loss as a congestion indicator. Then there was a proposal which was TCP Vegas. I don't know why. The first TCP congestion control algorithm was implemented in Tahoe, and since then people just stuck to different cities in Nevada. Now all new TCP variants, some researcher from MIT will come up with a TCP variant, and now they call it TCP Boston. Someone from UCLA comes up with a TCP variant, and it's called TCP Westwood. Westwood is the area where UCLA is. But initially all the TCP variants were some cities in Nevada. So TCP Vegas decided not to use loss as the congestion indication, but it used delay. Very recently, in the last couple of years, there has been this TCP variant called fast, coming out of Caltech, and that's again based on TCP Vegas, and it also uses delay as a congestion indicator. I don't know if you've been reading these press releases over the past few months that Caltech researchers break throughput record. Yeah, between Europe and the US. So the throughput record that's being broken is being broken by using this TCP variant called TCP fast. We'll see that the way Tahoe, Reno, New Reno, the way they react to congestion, this mechanism is not very good for links which have a high bandwidth but also high delay. And specifically for those links, delay based mechanisms are much better, and TCP fast tries to exploit that. But let's start with the loss as congestion indication based mechanisms. These mechanisms use this principle of additive increase and multiplicative decrease. Also called AIMD as the congestion control mechanism. So let's see how that works. So the way it works is if you plot the sending window, it's called let's say the congestion window as a function of time. You initially start, the sender will start with a certain value of the congestion window. So let's say it starts with a congestion window of 4 1K packets. In one round it's going to send these 4 packets out, and then it will wait for the acknowledgements to come back. If all the acknowledgements come back successfully, then it's going to increase this window additively. So if all of them come back successfully, then there's going to be a linear increase in this window. The window will go from 4 to 5. Now it sends out 5 packets, waits for the acknowledgements to come back. If all of them do come back successfully, then in the next round it's going to send 6. And it proceeds until the window size becomes larger than what the network can handle. And at that point there's going to be a loss. So the loss is detected by TCP either by duplicate acknowledgements or timeouts. And what the AIMD mechanism says is when the loss occurs, the decrease is going to be multiplicative. So you're going to increase additively, but you decrease multiplicatively. So when here, let's say loss occurs, all the acknowledgements do not come back successfully. At this point, TCP is going to reduce its window size. If the window size here was W, the window size becomes W over 2. So what is the idea? In every round, if TCP does not sense any congestion, if it does not get any loss, it increases the window size additively by 1 packet. If there is a loss, then it decreases the window size multiplicatively. So if your current window size is W, it makes the new window size W over 2, and then it starts again. Then it will continue increasing until there is another loss when it reduces W over 2. And so on and so forth. This figure is what's commonly referred to as the TCP sawtooth. Yeah.
Flow delay overtakes the congestion delay, then you never really get that financial later.
Yeah. So this congestion window, you assume that it's always lower than the advertised window or the receiver window. So you're dealing with scenarios where the bottleneck is the network, not the receiver. That's a good question. So when you actually implement TCP maintains this variable congestion window, and it also has the variable advertised window, which the receiver has advertised. Your actual window is going to be the minimum of these two. Okay, so TCP uses this mechanism of, yeah.
Well, does it matter how many packets are lost? Like it'll always have the congestion window, even if, let's say, one packet is lost, you could just decrease it by 1 instead of having.
So if one packet gets lost,
So why don't you decrease it by the number of packets that were lost?
okay. So what you're suggesting is additive increase and additive decrease. If one packet gets lost, decrease it by only 1. Decrease the window size by 1. That's an excellent question, and the answer to that is AIMD is a mechanism which guarantees fairness. If you don't do AIMD, if you do additive increase, additive decrease, then your resulting protocol is not going to be fair. So let's try and understand what fairness means. So these points, what do they indicate? That there is congestion in the network. So the total incoming rate to the network is more than what the network can handle. So that indicates that the senders, all of them, have to cut back their rate, reduce their rate, and adjust their rate. Now let's look at a scenario where there are two senders. So you have two senders. Let's say their rate is x1 and x2. We plot the rate of one sender on the x-axis as x2, the rate of the other sender as x1. And so suppose this was the sawtooth of the first flow. The second flow starts sometime now. here. So when the congestion occurs, its window size was somewhere here, and it will drop down to some point here. Let's see how that impacts fairness. So in a fair allocation, let's say these two flows are competing for bandwidth on a link. In a fair allocation, x1 should be equal to x2, right? So if you're plotting their respective bandwidths, then the fairness line is a line which goes in a 45-degree angle to the x-axis. Any bandwidth allocation on this line indicates that it's a fair division of resources, because here x1 is equal to x2. Okay. Now let's say the capacity of the link is some rate c. So you plot c here, c here. This line so this was the fairness and this is the efficiency line. So if you're operating anywhere on this line, that would mean that the capacity of the link is being fully utilized, right? Because on this line, x1 plus x2 is equal to c. So this is efficient utilization of resources. This is fair utilization of resources. Where do you want to be? You want to be here, where you have used up all the capacity that's available and it's equally divided between the flows. If you are anywhere here, that indicates an inefficient allocation. You're not fully using the capacity. If you are anywhere here, that means that you are in a state of congestion. x1 plus x2 is greater than c if your allocation is anywhere here. All right? Is that part clear? So now these flows, when they start out, they don't know what C is and they don't know who else they are competing with. So let's say at any point the rate of x1 is somewhere here. It started out earlier. Rate of x2 is somewhere here. So x1 plus x2 is this point. According to the additive increase scenario, what is going to be the next point if you are still uncongested? How is this point going to move? See, in the next round, x1 will become x1 plus 1, x2 becomes x2 plus 1, right? That's the additive increase principle. If there's no congestion, when you're operating here, when there's still available capacity, you're going to increase your window size by 1. So that is a vector which is parallel to this line. So it will go in an angle 45 degrees to the horizontal up. Okay? And eventually what will happen is this vector will overshoot your efficiency line. So now what happens? Now there is congestion. These flows will sense the congestion and reduce their rate. So when this rate reduction occurs, how does this point move? Where does it go after the rate reduction? So now what's going to happen? is x1 becomes x1 over 2 and x2 becomes x2 over 2. So how does this point move? It will move directly in the direction of the origin. So if you draw a line joining this point to the origin, the new point here is going to be somewhere here. It will move towards the origin. Why? Because the slope of this point is not going to change. You have just scaled this point down. So what you do is you move towards the origin. Now you reach an uncongested state. So you start the process again. You move 45 degrees and then you move towards the origin. Then you move 45 degrees and then you move towards the origin. So what that does is, no matter where you start from, the behavior of this algorithm is always to push you to this point. If you start from here, what's going to happen? You'll move 45 degrees to the horizontal in this direction and then you'll start moving here. So irrespective of where you start from, you'll finally end up at this point where you have a fair and efficient allocation of the resources. If you did anything else, if you did multiplicative increase and multiplicative decrease, or additive increase and additive decrease, you're not going to end up at this point. So what are the benefits of this algorithm? It's fair, it's efficient, and it's distributed. Each source just has to know whether it is in a congested state or whether it's in a congested state or uncongested state, and react accordingly. So this AIMD mechanism ensures fairness. So that answers your question? Okay. So all these mechanisms here which use loss as the congestion indication implement some sort of AIMD. There are implementation level details which sort of there are minor differences between the way Tahoe is implemented, the way Reno is implemented, New Reno is implemented. So all of them use loss as the congestion indication. How is loss interpreted at the TCP sender? Loss can be interpreted in two ways. What are the two ways? Yeah.
One is if you don't get an act back.
So one is if you don't get an ACK back and there's a timeout. What is the other way? You get duplicate acts. So timeout and duplicate acts. Which is the most severe form of congestion? Timeout. Timeout is the most severe form of congestion because duplicate acts indicate that although one data packet got lost, subsequent data packets were able to make their way through and generated duplicate acts. So this is a more severe form of congestion than this. So the behavior of TCP implementation is different if there's a timeout versus duplicate ACK. So AIMD is implemented when there's a duplicate ACK. If on the other hand loss occurs, which is a timeout, then the behavior of TCP is to drop this window down to 1. Doesn't matter where you started from. If there's a timeout, you drop the window down to 1 and then restart increasing from the window size 1. If the loss is dupack, remember TCP uses 3 dupacks, then you do the AIMD thing. But if it's a timeout, then you drop the window size to 1 because timeout indicates that there is severe congestion. Another implementation level detail is have you heard of this term called slow start? Nope. So most TCP implementations also implement this thing called slow start. So what slow start does is when you start this window off, it's actually a fast start. The name is confusing. When you start this window off from the minimum value, you increase not additively but exponentially, and at some point switch to additive increase. So the initial increase is exponential, and that's the philosophy behind slow start. So how is it implemented? Let's say your window size is W. So how many acknowledgements are you expecting? You're expecting W acknowledgements to come back. If your window size is W, you send out W packets, then W acknowledgements will come back. So if you're, let's say, doing additive increase, loss occurs at some window size W. If it's a triple duplicate act loss, a less severe kind of congestion, you reduce your window size to W over 2. You reduce your SS thresh to whatever W over 2 is. If the loss is a timeout kind of loss, you're going to reduce your window size to 1, but your SS thresh goes down to W over 2. And then you do the slow start business, come up there, and then do congestion avoidance. The difference between these variants of TCP is how, when do you switch, how do you interpret different losses. So in the next lecture we'll see what are the details of the implementations here. But the basic idea is the same. Additive increase, multiplicative decrease, and the use of slow start to quickly ramp up.